In this question, we're asked to draw the Lewis structure of PF5, and I added a TeBr4. So first we have PF5. First step, count valence electrons. 5 plus 5 times 7, 5 fluorines, 7 valence electrons each, which gives us 40 electrons. Put the least electronegative atom in the middle. Phosphorus is the most electronegative atom, which leaves, fluorine is the most electronegative atom, which leaves phosphorus to go in the middle. And we bond it to 5 fluorines, like so. Instantly, we notice there might be a problem. Before we even put in all the rest of the electrons, we notice there might be a problem because phosphorus has expanded its octet. It has 2, 4, 6, 8, 10 electrons around it. If we look at a periodic table, and we find phosphorus, it's in period 3 of the periodic table, which we can kind of see here. So phosphorus is here, it's in period 3 of the periodic table. This means that it can have an expanded octet. Period 2 elements cannot have a expanded octet, but period 3 and lower on the periodic table elements can. So phosphorus can have an expanded octet. Back to our Lewis structure, and I'll show you a way to check this. We have 40 electrons. 40 is evenly divisible by 8. 5 times 8 is 40. So if I put 8 electrons around each fluorine, 1 bond, and 3 lone pairs, I will have used 40 electrons. This is just a little trick that saves us counting time. It's not necessary. We can, of course, count all the electrons, but when there's 40 of them, I'd prefer not to. So we put 8 electrons around each fluorine, and now we have placed 40 electrons. As I've said in previous videos, one of the great things about Lewis structures is we can check our answers. And we check our answers through minimizing formal charges. So we've filled the octet on each fluorine. So each fluorine has a full octet. Now, what we need to do is check the formal charges. And again, we already talked about phosphorus having an expanded octet. So here, if we check the formal charge of fluorine, it wants to have 7 electrons around it, and it has, count the dots as 1, count the dashes as 1, 1, 2, 3, 4, 5, 6, 7. It's 0. Phosphorus is in 5a, so it wants to have 5 valence electrons around it, and it has 1, 2, 3, 4, 5. It's also 0. This, since phosphorus can expand its octet, this is a great Lewis structure. Now we have TeBr4. Tellurium, although a metalloid, can form covalent compounds, and here we have 6 valence electrons from tellurium, plus 4 times 7, which equals 34 electrons. Bromine is more electronegative than tellurium, so we put tellurium in the middle, and we bond it to 4 bromines. Tellurium has an octet, and now I want to go about filling all of the octets on bromine. I have now put 4 times 8, because there's 8 electrons around each bromine, there's 4 bromines, or 32 electrons in, which means I have 2 more electrons, because I have to place 34 electrons. So now my question becomes, do I put them on bromine, which can expand its octet, because it's far enough down on the periodic table, it's period 3 or lower, or tellurium, which can also expand its octet? The answer comes from formal charges. So let's look at bromine. Bromine, and they're all the same, wants to have 7 electrons around it. How many does it have? 1, 2, 3, 4, 5, 6, 7. Bromine's happy. It has a 0 formal charge. What about tellurium? Tellurium wants to have 6 electrons around it. How many does it have right now? 1, 2, 3, 4. This makes tellurium 2+. It's missing 2 electrons. That's not ideal. But I have 2 electrons left over. So why not put them on tellurium? The reason we put them on tellurium is it minimizes our formal charges. Now the formal charge of tellurium is 0. Wants to have 6 and has 1, 2, 3, 4, 5, 6. No formal charge. This is the best Lewis structure of TeBr4. We always just want to triple check that it can expand its octet, and tellurium is very far down on the periodic table, so it certainly can.